Okay, hello, this is Dr. Hanaa Assil, and this is the June 2022 paper of Unit 4 in the International AS of the Chemistry Pearson Edexcel. So let us take a look at this paper and discuss the questions and their answers. So the first section has multiple choice questions, and the first one says, how many peaks are there in the low resolution proton NMR spectrum of 2-methyl propane 2-ol? So first of all, we look at what is the structure of 2-methyl propane 2-ol. So this is it. And then we're looking at what? We're looking at the proton NMR. So we're looking at how many types of protons do we have. You do realize that the three CH3s are all the same proton. So all of these will give the singlet that is at the beginning. And then we have the H of the OH that also will give another singlet. So we have two peaks in the low resolution proton NMR of this compound. Okay, which compound has three peaks? So we want something that gives three peaks, and the relative peak areas are 3 to 2 to 1. So let's take a look at the structure of each of these. Propanal. What is the structure of propanal? That's it. Now, how many peaks in the proton NMR? You can see that we have three types of hydrogens. So this will give three peaks, and they are in the ratio of 3 to 2 to 1. So this is actually our answer. Now let's check the others. Propane, what is propane? This is propane. How many types of hydrogens do we have? We have two. The CH2 in the middle, that's one. That will give one peak, and the two CH3s on the ends are similar, so this will give another peak. So actually this one will give only two peaks. Now what about this one? This will give how many peaks? This actually gives four types of hydrogen, so we have four peaks. What about this one? This one will give the CH3s, that's one peak, the CH, that's another peak, and the OH is another peak. So actually this gives three peaks, but they are in the ratio of what? They are in the ratio of 6 to 1 to 1, not the 3 to 1 to 2 to 1 that he's asking for. So our answer is A. Please always check that if you choose one, check that the others are not correct. Okay, which compound does not have a singlet peak in its high resolution proton NMR? Okay, does not have a singlet peak. Let's take a look. Butanoic acid. Well, butanoic acid, this hydrogen of the acid will give a singlet. So this one is not our answer. What about butanone? Well, does it have a singlet? Yes, this will give me a singlet for the CH3 hydrogens. So this will have a singlet. What about this one? This one does not have a singlet because the hydrogen of the aldehyde, there are hydrogens on the neighboring carbon. So this hydrogen is not a singlet. So we don't have a singlet for this compound. So this is my answer. Butane 1-ol. Butane 1-ol will give a singlet for the hydrogen of the OH. Okay, the high resolution mass spectrum of an organic compound X has a molecular ion peak with 58 point something and another peak with 29 point something. So which compound is this? And he gives you the exact values for the atomic masses, and we're supposed to find out which one is the correct formula. Okay, let's take a look. A is propanone. So propanone, will it have what he's asking for? Well, if we calculate its MR is 58.0417, so it will have a molecular ion peak at that M over Z, but it does not have a peak for 29 point something. So this is not our answer. Okay, what about this one? This one is propanal, it does have a part that would give M over Z 29.0390, and the MR is the 58 point, what he's asking for. So this is actually our answer. The others, their MR are not 58, so they will not have a peak at 58 point some. A high-performance liquid chromatography system used a column with a non-polar stationary phase and a solvent of methanol and water. So the stationary phase is non-polar and the solvent is polar. Now, a mixture of octane, octanol, and octanol was placed in the HPLC column. What is the order of retention time? The solvent is polar, so the substance that is more polar will be carried faster, so it will have a shorter retention time. So what we're looking for is the one with the shortest retention time is the one that is most polar, and the one with the longest retention time is the one that is least polar, so that is D. A diagram of the thin layer chromatography of substance Y is shown. What is RF value of substance Y? Again, what do we mean by RF value? If we have a certain spot, we measure the distance from the baseline to that spot, and the distance of the baseline from the baseline to the solvent front, the RF value is the distance moved by the spot divided by the distance moved by the solvent. And remember that when we look at it, we don't even need to sit down and measure. You can see that it is almost 3/4 of the distance from the baseline to the solvent front. So looking at this, definitely our answer is not 1.33. RF values have to be always less than 1. Now, is it 0.25? 0.25 means the spot is very low, is only a quarter of the distance. 0.6 also is not correct, so it is 0.75. It's about 3/4 of the distance, and if we're not sure, we can measure the distance using a ruler. Which reaction cannot form a carboxylic acid? Cannot form a carboxylic acid. Okay, oxidation of primary alcohol. I want something that cannot form a carboxylic acid. Oxidation of primary alcohol. Well, if you oxidize a primary alcohol first, it would give you an aldehyde and then an acid. So this would form an acid. Acid hydrolysis of nitrile, you should realize that hydrolysis of nitriles will give acid. What about alkaline hydrolysis? Remember that alkaline hydrolysis will not give you the acid, it will give the sodium salt or a carboxylate salt. So we don't get the acid when we do alkaline hydrolysis. If we want the acid, we would need acid hydrolysis. Acyl chloride, yes, acyl chloride reacting with water would give the acid. Which alcohol could not be formed by the reduction of an aldehyde or a ketone? Could not be formed by reduction of an aldehyde or a ketone. Let's take a look. 2-methyl pentane 1-ol. 2-methyl pentane 1-ol, this could be formed by reduction of an aldehyde. This 3-methyl pentane 2-ol, yes, if I do reduction of a ketone. 3-methyl pentane 3-ol, remember this is tertiary alcohol, you cannot form it by reduction of an aldehyde or a ketone. So this is my answer. 2-methyl pentane 3-ol, yes, you can form it by reduction of a ketone. Okay, what is the pH of this solution of carbonic acid? And he gives me the Ka of the carbonic acid, and he wants the pH, and he gives me the concentration. You should realize the concentration of H plus ions, which I'm going to use to get the pH. Concentration of H plus ions is the square root of the Ka times concentration. So from that I can get the H plus concentration of H plus ions. Concentration of H plus ions would be the Ka times the concentration, square root of that, that gives me a certain number. I can use that to get pH. Do you remember? pH is minus log concentration of H plus ion. So minus log of that number gives me a pH of 4.17. What is the pH of this solution of sodium hydroxide? And he gives me that the Kw is 10 to the minus 14. Okay, so he wants pH of a solution of sodium hydroxide. Well, you know that sodium hydroxide, when it ionizes, this is a strong base, so it will give sodium ions and OH minus ions. So actually the concentration of the hydroxyl ions are the same as the concentration of the sodium hydroxide solution. So that is my concentration of OH minus. Now, from that, I can get the concentration of H plus, because I know that H plus times OH minus will give the Kw. So from concentration of H plus ions, I can get the pH. The pH is minus log concentration of H plus ions. So this gives me a pH of 13.43. A 0.1 mole per decimeter cubed aqueous acid solution was added to 25 centimeter cubed of 0.1 mole per decimeter cubed aqueous solution of an alkali, and he gives me the titration curve for that. Which titration would produce this curve? Well, I look at this. He's given me a series of acids and bases, and he's asking which of them was used to produce this curve. Well, let's look at the curve. You can see that the curve starts with a weak base, something around pH 10 or something. So that's a weak base. And it ends with pH of around 1 or 2. So that's a strong acid. So what I'm looking for here is a strong acid with a weak base. Of course, which one is stronger, ethanoic or hydrochloric? Well, you should realize hydrochloric is strong acid. So I want an answer that has hydrochloric acid added to a weak base. Which of these is a weak base? Of course, you should know that ammonia is the weak base. Which indicator would be the most suitable for this titration? Well, let us look. The pH at neutralization point is about pH maybe 5 or 6. So I'm looking at something that will have a pH range about 5 or 6. So that is the methyl red. 4 graphs are shown. Which graph shows the rate of reaction on the vertical axis plotted against concentration of the reactant on the horizontal for a zero order? So which of these is for a zero order? You should be familiar which graph, if I'm plotting. Remember, we're plotting rate versus concentration of reactant. You should realize that graph 1 is what we get if it is second order. Graph 3 is the one that we get for zero order, and graph 4 is actually what we get for first order. Please learn that if we don't know. Now, the next question says which graph shows the rate on the vertical and concentration on the for a first order. Remember, we said which of these is for first order? Graph 4 is for first order. Propanone reacts with iodine in the presence of a sulfuric acid catalyst. Which method would be most suitable for following this reaction? Okay, what's happening here? We're reacting something with iodine and it changes to iodide. I want you to remember that iodine with iodide, you use colorimetry because you are measuring the change of the color of iodine, which is dark blue black, with HI, which would be a colorless solution. The rate equation for this reaction is this, and he says 2 experiments were carried out. In both experiments, the concentration of propanone and iodine remains the same, but the concentration of acid was changed. The initial rate in the first experiment was 3 times faster than the initial rate in the second experiment. In the first experiment, the initial pH was 1.5. What is the initial pH in the second experiment? Okay, so we know that rate is directly proportional to concentration of H plus ions. And he's saying the initial rate in the first one was 3 times faster than the second. So if the pH in the first experiment was 1.5, what would be the pH in the second experiment? So remember that concentration of H plus ions is 10 to the minus pH. So for the first experiment, the concentration of H plus ions is 0.0316. Now, if the first experiment was 3 times faster, then the second experiment would have a concentration of H plus ions that is a third of that, and that means the pH for that would be 1.98. Are we following? Okay. The next question says a series of experiments was carried out to determine the rate constant K of the reaction between bromate ions, bromide ions at different temperatures. A graph of length K was plotted against 1 over T, and the gradient was this. The Arrhenius equation may be written as this. Remember, how do we get activation energy from all of this? Remember that for this kind of graph, the energy of activation is minus gradient times R. He already gives me the gradient. R is 8.31. So I have activation energy, but this comes out in joules. So it is 38.8 kilojoules per mole. Solid vanadium oxide catalyzes the equilibrium shown. Which statement is correct? So we have a reversible reaction. And he's saying which of these is correct. So, okay, vanadium oxide is a homogeneous catalyst. Do you remember the meaning of homogeneous or heterogeneous? Okay. Homogeneous is if the catalyst is the same state as the reactants. But here we have the catalyst is solid. He says it's solid vanadium oxide, and vanadium oxide is a solid. And we're using it to catalyze reactions that are in the gaseous state. So actually, it is heterogeneous catalyst, not homogeneous. So A is wrong. Decreasing the pressure would increase the yield of sulfur trioxide. Well, let's see. Decreasing the pressure means we're going to open up the volume, and decreasing the pressure means it will go to the side with more number of moles. So actually, if we decrease the pressure in this reaction, it will go backward to give larger number of moles, and that means the yield of sulfur trioxide would actually decrease, not increase. So B is wrong. Increasing the surface area of the catalyst would increase the equilibrium yield. Remember that. Catalyst does not affect the yield. It only affects the rate of the reaction, causes both forward and backward reactions to be faster, but it does not affect the yield. So C is wrong. Decreasing the temperature would increase the yield of sulfur trioxide. Well, let's see. The delta H is negative, and that means the forward reaction is exothermic, and that means if I decrease the temperature, yes, it would go, or the equilibrium would shift to the right, so this will increase the yield of sulfur trioxide. Okay, in which series does the standard molar entropy of the compounds increase? So which of these has the entropy increasing? Remember, if I'm comparing between solid, liquid, and gas, the solids will have less entropy, liquids will have more, gas will have more. So solid, liquid, gas, we are choosing between A and B. Now, the next choice would be which one would have more entropy, CO2 or SO2? Well, you should realize that more complex molecules have higher entropy, and that means if I have CO2, this is something that has a total number of electrons 22. Sulfur dioxide has a total number of electrons of 32, and that means the sulfur dioxide would have higher entropy than carbon dioxide. Experimental lattice energy values determined using the Born-Haber cycle often differ from calculated theoretical values. The ionic radii and charges of some ions are shown. So he has ions which he calls PQRS. and he gives me the ionic radius, and he's saying which of these compounds would be expected to show the largest percentage difference between experimental and theoretical lattice energies. Well, you should realize which type of compounds have larger difference between experimental and theoretical. You should realize that the one with more covalent character. So the one that is more likely to have more ion polarization is the one that is more covalent, and it's the one that will have a larger difference between experimental and theoretical. So which of these are more likely to have ion polarization? Well, let's take a look. If we're looking at the cations, the positive ions, which one do we want? We want the one that is smaller radius, because that will have greater charge density. So P or Q, it is P. Now, if we're looking at the anions, the one with larger ionic radius is more easily polarized. So the one with larger is S, and that means the one with more covalent character is the compound between P and S. This question is about ammonia and ammonium chloride. Ammonia is produced by reacting nitrogen and hydrogen, and he's saying write the expression for the equilibrium constant Kp. Remember that Kp has to do with partial pressure, and it is the partial pressure of the products to the power of their coefficient over the partial pressure of the reactants to the power of their coefficient. So this is the expression for Kp. Then he says an equilibrium was established by mixing nitrogen and hydrogen in 1:3 ratio by volume at a temperature of 450 degrees Celsius and pressure 280 m. The equilibrium mixture contained 28% by volume. So he already tells me that the mole fraction of ammonia is 0.28. Now, the rest of the 1 mole, remember that the total of the mole fractions should be 1. Now, if ammonia is 0.28 and the others are in a ratio of 1:3, then these will be the mole fractions of nitrogen and hydrogen. Okay, then he wants partial pressure of each one. How do we calculate the partial pressure of each one? It is the mole fraction times the pressure. He already gives me up there, the pressure is 280 m. So the partial pressure for each one is its mole fraction times 200. So 0.18 times 200, 0.54 times 200, and so on. So this is the completing the table. And then calculate the equilibrium constant. Of course, we said this was the expression for the equilibrium constant. Now, looking at the table, it gives me the values for each partial pressure. We put it into the equation to the power of its coefficient. We get this value for K. He wants units. Remember that for all of these, usually he wants units. So let's take a look. Well, this is atmosphere to the power 2 over atmosphere to the power 4, and that means the overall unit is atmosphere to the power minus 2. When the temperature was reduced to 400 degrees Celsius, the same pressure, the equilibrium mixture contained 36%. So we are lowering the temperature and we are increasing the amount of ammonia. And that means if he's lowering the temperature, the ammonia increases. That means the forward reaction is exothermic, because when he lowered the temperature, the equilibrium shifted to the right and we obtained a higher yield of ammonia. So the forward must be exothermic. Ammonium chloride can be produced by reacting ammonia with hydrogen chloride. Ammonium chloride is a white solid that is very soluble in water. Hess's law can be used to calculate the enthalpy of solution of ammonium chloride using hydration enthalpies and lattice energy. So he's saying complete the Hess's law. Now, what does he have? The lattice energy is the change from NH4 plus Cl minus to the solid form. That's the lattice energy. Now, what is the hydration energy? The hydration energy is changing the gas into aqueous. So ammonium from gas to aqueous and the chloride from gas to aqueous. Complete the expression for the enthalpy change of solution. So how do we get the enthalpy change of solution? You should realize, looking at the direction of the arrows, that the lattice energy plus delta H of solution, that gives you delta H of hydration. So he wants the delta H of solution. Delta H of solution would be the delta H of hydration minus the lattice energy. Calculate the enthalpy change of solution. Okay, so we already decided that this is the equation. Now we just put the numbers in there and we get delta H of solution of plus 20 kilojoule per mole. A student suggested that the enthalpy change of solution would be of ammonium bromide would be of similar magnitude to that of ammonium chloride. Comment on this suggestion. Okay, so if we say we're doing ammonium bromide instead of ammonium chloride, well, enthalpy of solution depends on both the enthalpy of hydration and the lattice energies, because we said delta H of solution is delta H of hydration minus lattice energy. Looking at the ions, you can see that bromide ions would be larger than the chloride ions. So the hydration enthalpy of bromide is less exothermic than chloride ions. But then the lattice energy of ammonium bromide is less exothermic, and the lattice energy, that means minus of minus, it's a minus in the equation. So minus of something that is already less exothermic, this will cancel each other, so the enthalpies of solution should be similar. Write an ionic equation to show why aqueous solutions of ammonium chloride are acidic. You don't want state symbols, so remember that ammonium ions in water will give ammonia plus an acid, so this would be written either as H3O plus or just ionization or breakdown of the NH4 plus to give NH3 plus H plus ions. This question is about carbonyl compounds. Three carbonyl compounds A, B, and C are straight chains. So we're looking at things that are straight chains. And they have a formula of C5H10O. So that's 5 carbons. The first one, he says, A reacts with Tollens reagent to give a silver mirror. Remember, Tollens reagent is a test for what? It's a test for aldehyde. So A must be an aldehyde. B reacts with iodine in presence of alkali to produce yellow crystals. This was test for what? This was test for the presence of a C double bond O with a CH3 next to it. So this is the structure of B. And then C is another structure that has also a carbonyl, and that will have to be in the middle of the compound. Another carbonyl compound, propanal, reacts with HCN in presence of KCN to form a racemic mixture of two optical isomers of this. And the first question says, give the IUPAC name for this. Okay, this is the molecule he's talking about. Now, what is the IUPAC name for that? 2-hydroxybutane nitrile. Remember that the CN group is called nitrile. Describe how you could distinguish between pure samples of the two optical isomers. If we have two optical isomers, then they will rotate the plane of polarized light in opposite directions. That is the difference between optical isomers. Explain with reference to the reaction mechanism why this reaction produces a racemic mixture. This is the compound he's talking about, and we're saying we're going to attack cyanide on the carbonyl, and we should know that the carbonyl carbon is planar, so the cyanide can attack from either side to the same extent. So it will produce equal amounts of the two optical isomers that forms a racemic mixture. Propanone, an isomer of propanal, also reacts with HCN in the presence of KCN. Draw the skeletal formula of the product. So he's starting with propanone. This is propanone. We're reacting it with HCN of KCN. That means we're adding cyanide on that compound. So this is my product. But he wants the skeletal formula. So how do you draw this as a skeletal formula? This is the skeletal formula of the product. State why the product formed does not show optical isomerism. What is he talking about? He's talking about this product. And he's saying it's not an optical isomer. Of course, it's not an optical isomer, because in order to be an optical isomer, we should have a chiral center in which the carbon is bonded to 4 different groups. But here, the carbon is bonded to 2 similar methyl groups. So this is not a chiral center. It will not form an optical isomer. Carbon-13 NMR spectroscopy provides information about the structures of propanal and propanone. Identify the chemical shift range and carbon environment of one peak you would expect to see in both propanal and propanol. What is the difference between propanal and propanol? These are the 2 compounds. He wants a peak that is present in both. Of course, the peak that is present in both is the peak for the carbonyl. Now, if we look at the data booklet, you will find that the carbonyl of whether a ketone or an aldehyde is within this range. Okay? State the number of peaks you would expect to see in each carbon-13 NMR of propanal and propanol. Okay, let's take a look at propanal. How many different carbon environments do we have? We have the CH3, that's 1 carbon, the CH2 in the middle, that's another carbon, and the carbonyl. So I have 3 peaks in the carbon-13 NMR of propanal. While in propanone, what do we have? We have only 2, because the 2 CH3s are similar. So the 2 carbons of the CH3s are similar, and then the carbon of the carbonyl, so we'll have only 2 peaks. Compare and contrast the reactions of ethanoyl chloride with water, ethanol, and ammonia. Refer to the structural features of the molecules that determine the type of reaction. Identify the products, and you may include equations. Okay, let's take a look. Ethanoyl chloride is this. I want to react it with what? With water? Well, this gives the acid, so this will give ethanoic acid plus HCl. What if we're reacting it with ethanol? Well, when the alcohol reacts with the acid chloride, we have ester. So this is ethyl ethanoate plus HCl also. If we're looking at the carbon ethanoyl chloride with ammonia, this gives you the amide. So this will give ethanamide. So these are different products. These are the names of the different products, but they all, what happened is in all of them, the lone pair of electrons, because he wants the type of reaction, lone pair of electrons on the nucleophiles attack the carbonyl carbon. So this is a nucleophilic reaction to form HCl. So all of them form HCl. They give different products, and we wrote the names of each product. All of them are fast reactions. Remember that acid chlorides react very quickly at room temperature. This question is about methanoic acid and propanoic acid. A student carried out a titration to find the concentration of an aqueous solution of potassium hydroxide. So he has this volume of this concentration of methanoic acid. He pipetted it into a conical flask. Potassium hydroxide was added from a burette while measuring the pH. First of all, complete the equation for the reaction. What is he reacting? He's reacting methanoic acid with potassium hydroxide to give the potassium salt plus water. So this is the equation. Then he says calculate the concentration of potassium hydroxide solution using your equation and the titration curve. Well, let's take a look. The volume of the potassium hydroxide at neutralization, the volume from the graph is 22. And we know that he wants the concentration of potassium hydroxide. So we get the number of moles of potassium hydroxide. This is the same as the number of moles of the methanoic acid. He gives me information about methanoic acid. Remember, from the equation, the ratio was 1:1. So the number of moles of methanoic acid is the concentration times the volume that he gave me, and that is the same as number of moles of KOH. Then I can get concentration of the KOH. Remember that the volumes that have to be included in all of these reactions are, or in all of these equations, are in decimeter cubed. So the 22 is actually 0.022. Okay, use the titration curve to determine a value for Ka. Okay, how do we get Ka? We look at this, and you should realize that we have an equation that says concentration of H plus ions is square root of Ka times the concentration. And that means that to get Ka, it will be concentration of H plus ions to the power 2 over concentration of the solution. So we have the pH. We look at the initial pH of the methanoic acid that we started with. From the graph, it is about 2.3. It's not very clear, but it's an estimation of 2.3. So if we say that the pH is 2.3, I can get the concentration of H plus ions. It's 10 to the minus pH. And that means I can put that into my equation. He already tells me up there. If I look up, I find that the methanoic acid has a concentration of 0.15. So I can use that in the equation to get Ka. A student prepared a buffer by mixing together equimolar aqueous solutions of propanoic acid and sodium propanoate. So here he's preparing a buffer. The acid dissociation constant Ka for propanoic acid is this. Calculate the volume ratio of propanoic acid to sodium propanoate needed to produce a buffer solution with a pH of 4.6. Again, what are we talking about? He gives me the Ka. I can use it to get the pKa. So the pKa is 4.8861. Then we have an equation that says the pH is equal to the pKa plus log of the ratio. But here the ratio is the ratio of the salt to the acid. So this is the equation that we have. We can put the pKa into that equation, and we have a pH of 4.6, and I can get that ratio. So from the equation, the ratio log of A minus over H plus is this, so I can get A minus over HA, but he wants HA to A minus, so this is 1.9321. Okay. This question is about hydrolysis of 2-bromobutane with aqueous sodium hydroxide. The data shown were obtained in an experiment to investigate the kinetics of this reaction. And then he says, deduce the order of reaction with respect to 2-bromobutane and with respect to the hydroxide ions. Okay, when we have this kind of table, we look at two experiments in which one of them is constant and the other is changing. So if we look at experiment 1 and 2, we find that the concentration of hydroxide ions is constant. So we look at the other one. The other one has doubled. What happened to the rate? The rate doubled. If this doubles, then the order is first order. So with respect to the alkyl halide, it is first order because we're looking at experiment 1 and 2. Hydroxide ion is constant, the other doubles, the rate doubles. Then we want with respect to the OH minus. Okay, we choose the two experiments in which the alkyl halide is constant. So experiment 1 and 3, the 2-bromobutane is constant. What happened to the OH minus? Well, the OH minus doubled. Now, what happened to the rate when we doubled the OH minus? Nothing. The rate remained the same, and that means it is zero order with respect to OH minus, because from experiment 1 and 3, the 2-bromobutane concentration is constant. When the OH minus doubles, the rate remains the same. This is how we explain. You need to explain, justify your answers. So from that, he's saying write the rate equation. Of course, the rate would be just with respect to the bromobutane. So rate is K times concentration of the bromobutane. Then he says calculate the rate constant for experiment. So looking at experiment 1, we put in the values for the concentration and the rate to get K, and this comes out to be a certain number. Remember the units, we have to put them in. The concentration is mole per decimeter cubed, and the rate is mole per decimeter cubed per second, and that means the overall unit is seconds. Draw the mechanism for this reaction that is consistent with your rate equation. So looking at the rate equation, we said that the rate depends only on the concentration of the alkyl halide, and that means we're talking about an SN1 mechanism. So we remove the Br. Remember the dipoles. Carbon is slightly positive, the bromine is slightly negative, so the electrons in the bond go to the bromine. That forms a carbocation that is attacked by the hydroxide ions, and we end up with the alcohol and the bromide ion. Then the next question says the equation for reduction of iron 3 oxide by carbon is shown, and he wants to calculate the standard enthalpy change for the reaction. How do we get delta H of the reaction? You should remember that it is the total delta H of the products minus the reactants. So we have 2 times 0 for the iron, 3 times minus 110.5 for the CO, minus the reactants. This comes out to be a positive number, so please put in the sign. Then he says calculate the entropy change for this system. Again, the entropy change is the entropy of the products minus the reactants, and that gives me again a positive value. Calculate the temperature at which this reaction becomes feasible. Okay, we should know that I can use the delta H to get delta S of surroundings, and from that I can know that the delta S total is the total of the delta S surroundings plus delta S of system. When the reaction is feasible, the delta S total has to be 0 or a positive value. So the minimum temperature in which this reaction is feasible is if the delta S is 0 or above 0. So put in the delta H. Remember that the delta H was given in kilojoules while the delta S system was given in joules. So we have to fix these units. That gives me this kind of value. I can use it to calculate T. This comes out to be about 907.5 Kelvin, and that means this is the minimum temperature. So the temperatures must be higher than this value for the reaction to be feasible. The equation for the reduction of this reaction is shown. The entropy change delta S system is given. So he gives me that delta S system is plus 15.2. Explain why the reaction should be feasible at any temperature. Well, delta S system, he gives it to me as positive. And he gives me the delta H is negative. So the delta S of the surroundings is minus of a negative number. So the delta S of the surroundings is positive. And that means both of them are positive, and that means the delta S total is always positive, and the reaction is always feasible. Explain how an increase in temperature would affect the delta S total of this reaction. Well, you know that the delta S surroundings is minus delta H over T. And that means at higher temperatures, the delta S surroundings would decrease. But then the delta S system does not change. The delta S total is equal to delta S surroundings plus delta S system. So if the delta S surroundings decreases, that means that the delta S total would decrease. Here he's given me data in a table to construct a Born-Haber cycle for iron 2 oxide, and he gives me the values for each delta H, and he's saying complete the Born-Haber cycle by putting letters in the boxes to label the energy changes. Okay, let us take a look at these energy changes. Which one is A, B, C, D, and so on? You should realize that A is the entropy change of atomization from Fe solid to Fe gas. B is the first ionization energy of iron, that is changing Fe to Fe plus. H is the entropy change of atomization of oxygen, because we have O2, half of O2 changing to O gas from molecule to atom, so this is atomization. E is the first electron affinity of oxygen, so changing O to O minus. F is the second electron affinity, changing O minus to O2 minus. And G is the lattice energy from gases to solid. And of course, we said D is the entropy change of formation of the iron 2 oxide. So these are the different entropy changes. Now calculate the value for C. C was the second ionization energy of iron. So looking at all the arrows, please pay attention to the direction of the arrows. You will find that C is D minus the addition of all the rest. So we're just putting the numbers that he gives me in the table. So these are the numbers that he gives me in the table. Please be careful with the sign. So overall, C comes out to be a plus or a positive value. Suggest why the second electron affinity of oxygen is positive. Remember, second electron affinity is always positive because you're adding an electron to a negative ion, so something that has already an extra electron, we're adding another electron, so more energy is needed to overcome the repulsion between the negatively charged electrons. Okay, that's the end of this paper. I hope this was useful to you, and thank you for listening.